All right, let's dive in. Today, we're going deep, really deep into the quantum world, specifically atoms.
Yeah, like the absolute fundamentals of how atoms work, the quantum mechanics behind them.
Exactly. You gave me this really interesting chapter, Quantum Mechanics Basic, Atomic Structure, and I have to admit, some of it's a bit over my head. So I figured, who better to break it down than, well, you?
Well, I'm happy to try. We'll try to extract the key principles that govern atomic structure, starting from that infamous Schrödinger equation, but in 3 dimensions, no less, all the way to, well, things get a little spooky near the end with quantum entanglement.
Sounds good. Let's
Yeah.
go. So jumping right in, this chapter starts by expanding quantum mechanics into the three-dimensional world.
Right, because that's the world we actually live in, 3 dimensions.
No.
So it starts with the three-dimensional Schrödinger equation.
Uh-oh. Equations already.
Don't worry, I won't write it all out. But basically, it looks a lot like the one you've probably seen before, but with a few extra terms for y and z.
Makes sense. 3 dimensions.
Exactly. The key thing here is the wave function, which is a function of x, y, z, and t for time. It's a mathematical description of a quantum particle state.
Okay, and what does it tell us?
Well, it doesn't pinpoint the particle's exact location. It's more about probabilities. You square the wave function, get s, and that gives you the probability density, the likelihood of finding the particle in a tiny, tiny region of space at a given time.
So it's like a quantum weather forecast. Not where the particle is, but where it might be.
Kind of, yeah. And to make sure those probabilities make sense, you have the normalization condition.
Normalization.
Yeah, it ensures the total probability of finding the particle somewhere in all of space is 100%. Or 1, The particle has to be somewhere. It can't just disappear.
Right, it can't just vanish.
Yeah.
That makes sense. Then the chapter talks about stationary states. What are those?
Well, think of them as like the stable energy levels of the system, like rungs on a ladder. For these states, the probability distribution of finding the particle doesn't change with time. It remains stationary.
So even though things are happening at the quantum level, the overall picture stays the same.
Exactly. And they satisfy what we call the time-independent Schrödinger equation, where the energy of the state is constant.
Got it. So stationary states, they're stable. Now the chapter dives into a specific example. A particle trapped in a cubical box.
Yeah, the classic particle in a box scenario, but now in 3D. It's a good way to understand how quantization works in 3 dimensions. The particle can't escape, and it turns out it can only have specific discrete energy levels.
Quantized.
Yeah, like it can only be on certain rungs of the energy ladder, not in between.
Okay, so how do we figure out those energy levels?
Well, the wave function for the particle can be broken down into 3 parts, one for each dimension. X, Y, and Z.
So it's like the particle's motion is kind of separated in each direction.
You got it. And this leads to 3 quantum numbers, nx, ny, and nz, which are positive integers.
So each quantum number describes the particle's state in one of the dimensions.
Exactly. You put those 3 quantum numbers together, and you get a specific energy level for the particle.
So it's like a unique code for each energy state.
Yeah, that's a good way to think about it. And the formula for these energy levels depends on all 3 quantum numbers and the size of the box, of course.
Makes sense. Bigger box, lower energy level.
Exactly. More space for the particle to move around in. Now here's where it gets a little more complex. Degeneracy.
Degeneracy. Sounds a bit ominous.
Well, it just means that different states with different sets of quantum numbers can have the same energy.
So different quantum states, same energy. Why does that happen?
Think about the symmetry of the box. It's a perfect cube, so if you, say, switch the quantum numbers for x and y, it doesn't actually change the energy. But if you make the sides of the box different lengths, that symmetry breaks, and those degenerate states split into different energy levels.
So symmetry leads to degeneracy.
Exactly. Break the symmetry, lift the degeneracy, and that's just for the particle in a box. The chapter then goes to a much more realistic example, the hydrogen atom.
1 proton, 1 electron. The simplest atom.
Exactly. And because the interaction between the proton and electron is spherically symmetric, it only depends on the distance between them. It's much easier to work with spherical coordinates.
So instead of x, y, and z, we use radius and angles.
Exactly. R, theta, and phi. And something amazing happens here. When you solve the Schrödinger equation for the hydrogen atom using these coordinates, the quantization of the electron's orbital angular momentum just pops out naturally.
Wait, so the math itself says angular momentum is quantized.
Yeah, it's not something you have to force in the older Bohr model. And this leads to the introduction of 3 new quantum numbers.
Oh boy, more quantum numbers. Hit me.
First, there's the principal quantum number, n, good old n, just like in the Bohr model, it determines the energy level. N can be 1, 2, 3, and so on, going up in energy.
Higher N, higher energy. Got it. What's next?
Then we have the orbital quantum number, L. It can take on values from 0 up to n minus 1, and it tells you about the magnitude of the electron's orbital angular momentum.
So if N is 2, L can be 0 or 1.
Exactly. We often use letters for LS, for LA0, P for LO1, D for LO2, and so on. It's like different types of orbitals with different shapes.
Right, like S orbitals are spherical and P orbitals are dumbbell-shaped. I remember that from chemistry class.
Exactly. Finally, we have the magnetic quantum number, MLO. This one tells you about the orientation of the electron's orbital angular momentum in space.
Orientation.
Yeah, like which way the angular momentum vector is pointing, specifically its component along the z-axis.
Got it. So N for energy, L for the shape and magnitude of angular momentum, and ML for the orientation.
You got it. Now, because the force in the hydrogen atom is spherically symmetric, states with the same N but different L and ML have the same energy. We call that degeneracy again.
Symmetry strikes again.
Yep. But the chapter also points out that as N increases, the average distance of the electron from the nucleus also increases, so we get these electron shells.
Shells, like the layers of an onion.
Kind of. The principal quantum number N defines the shell. NO1 is the K shell, N-2 is the L shell, and so on. And within each shell, you have subshells, which are determined by L.
So for N2, L0 is the 2's subshell, and L1 is the 2p subshell.
Exactly. Higher shells, higher energy, further from the nucleus. And remember, we're not talking about those neat little orbits of the Bohr model.
Right, these are more like fuzzy clouds of probability.
Exactly. And to understand how this probability varies with distance from the nucleus, we have something called the radial probability distribution function, PIR. It tells you the probability of finding the electron at a specific distance, r, from the nucleus.
So it factors in that there's more volume further away from the nucleus.
Precisely. Now, things get even more interesting when we throw in an external magnetic field. That's when we get the Zeeman effect.
The Zeeman effect, what happens there?
Well, any moving charge creates a magnetic field, right? And the electron orbiting the nucleus has angular momentum, which means it acts like a tiny magnet.
So it has a magnetic moment.
Exactly. And this magnetic moment interacts with the external magnetic field. This interaction changes the energy of the electron, and the amount of change depends on ML, the magnetic quantum number.
So different ML values lead to different energy shifts.
Yes, and that's what causes spectral lines to split into multiple components. A single energy level splits into 2L plus 1 sublevels in the presence of the magnetic field. We call that the Zeeman effect.
So one spectral line becomes many.
Exactly. And the number of lines depends on L. Now, the chapter talks about something called the normal Zeeman effect.
Normal. So there's an abnormal Zeeman effect.
You could say that. The normal Zeeman effect predicts that a spectral line should split into 3 equally spaced lines. But experiments showed even more splitting, and that led to the discovery of electron spin.
Spin, like the electron is spinning like a top.
Well, it's not quite spinning in the classical sense, but it does have an intrinsic angular momentum, which we call spin. And this spin is quantized too. It's either spin up or spin down.
So two possible spin states.
Exactly. And this spin, it also creates a magnetic moment. And here's the thing, it's about twice as strong as the orbital magnetic moment. That's a bit of a mystery from a classical perspective, but it pops right out of relativistic quantum mechanics.
Okay, so electrons have both orbital and spin angular momentum, each with its own magnetic moment. And when you put that together with the external magnetic field, you get even more complex splitting pattern.
Exactly. We call that the anomalous Zeeman effect. And it's not just external magnetic fields that matter. The chapter then introduces spin-orbit coupling.
Spin-orbit coupling. What's that about?
Well, you have to think about it from the electron's perspective. As it orbits the nucleus, it sees the nucleus moving around it.
So relative motion.
Right, and that relative motion creates a magnetic field from the electron's point of view. And guess what? That magnetic field interacts with the electron's spin magnetic moment.
So the electron's own spin interacts with the magnetic field created by its own orbital motion.
Exactly. We call that spin-orbit coupling. And it leads to even finer energy splittings, what we call the fine structure of the spectral lines.
Wow, it's amazing how much detail there is.
Right. And to account for this, we introduce the concept of total angular momentum, J, which is the vector sum, the orbital and spin angular momenta.
So J equals L plus S.
Got it. And there's a quantum number for J, lowercase j, which can take on values based on L and S. And the energy levels, including the fine structure, now depend on both N and J.
And just when I thought we were done with energy level splitting, the chapter mentions hyperfine structure.
Right, we're going even deeper now. Hyperfine structure arises from the interaction between the electron's magnetic moment and the magnetic moment of the nucleus.
Wait, the nucleus has a magnetic moment too.
It can, yes. Many nuclei have a spin, and that spin creates a magnetic moment. And that tiny nuclear magnetic moment interacts with the electron's magnetic moment, causing these hyperfine splittings.
It's amazing how much complexity there is at the atomic level. Okay, so we've covered single electron atoms in great detail. What about multi-electron atoms?
That's where things get really complicated. Because now you have all these electrons repelling each other, it's basically impossible to solve the Schrödinger equation exactly for more than one electron.
So what do? Give up.
Not quite. We use approximations. The chapter introduces the central field approximation.
Central field approximation.
Yeah, it basically assumes that each electron moves in an average field created by the nucleus and all the other electrons. It's like smearing out the charge of the other electrons into a spherically symmetric cloud.
So it simplifies the problem by ignoring the detailed interactions between each pair of electrons.
Exactly. It's a way to make the math more manageable. But even with this approximation, we need another crucial principle, the Pauli exclusion principle.
Pauli exclusion principle. I've heard of that one.
It's one of the most important principles in quantum mechanics. It states that no two electrons in an atom can have the same set of quantum numbers.
So each electron needs its own unique quantum address.
Precisely. And this principle dictates how electrons fill up the energy levels in an atom. Electrons want to be in the lowest energy states possible, but because of the exclusion principle, they can't all pile into the same state.
So they have to spread out into different orbitals and shells.
Exactly. And this is the foundation of the periodic table. Elements in the same group have similar chemical properties because their outermost electrons, the valence electrons, have similar configurations.
So the Pauli exclusion principle explains why the periodic table is organized the way it is.
It's a big part of it, yes. And for atoms with just one valence electron, the chapter introduces the concept of effective nuclear charge.
Effective nuclear charge.
Yeah, because the inner electrons shield the outer electron from the full positive charge of the nucleus. So the valence electron feels an effective nuclear charge that's less than the actual nuclear charge.
Makes sense. Now, shifting gears a bit, the chapter talks about X-ray spectra. How do X-rays fit into all of this?
X-rays are great for probing the inner structure of atoms. When you bombard a material with high-energy electrons, they can knock out inner shell electrons from the atoms.
So you create a vacancy in one of the inner shells.
Right. And then an electron from a higher energy shell can drop down to fill that vacancy, and in the process, it emits an X-ray photon. The energy of that X-ray tells you about the energy difference between the two shells involved.
So it's like a fingerprint of the atom's energy levels.
Exactly. We call these characteristic X-rays because they're unique to each element. And there's a law, Moseley's law, that relates the frequency of the X-ray to the atomic number of the element.
So we can identify elements based on their X-ray spectra.
Absolutely. And the chapter also mentions X-ray absorption edges, which occur when the X-ray energy is just enough to knock out an inner shell electron completely. The energies of these absorption edges also tell you about the binding energies of the inner electrons.
Okay, so X-rays are like little probes for investigating the inner workings of atoms. Finally, we come to the weirdest part. Quantum entanglement.
Ah, yes, quantum entanglement. This is where things get really strange, even for quantum mechanics. It's about the idea that two or more particles can be linked together in a way that their fates are intertwined no matter how far apart they are.
So if you measure the state of one entangled particle, you instantly know something about the state of the other particle, even if they're miles apart.
Exactly. And it's not just that you know something about it, it's like the act of measuring one particle forces the other particle to take on a specific state.
That sounds like something out of science fiction.
It does, and Einstein himself was very uncomfortable with this idea. He called it spooky action at a distance. But experiment after experiment has confirmed that entanglement is real.
So is this like faster than light communication?
That's the catch. While the correlation between entangled particles seems to be instantaneous, you can't actually use it to send information faster than light. The outcome of measuring any individual entangled particle is still random, so you can't control it in a way that would allow you to send a message.
So it's a correlation, but not communication.
Exactly. But even though you can't send messages with it, entanglement is still incredibly useful, especially in the field of quantum computing.
Quantum computing, how does that work?
Quantum computers use qubits, which are like classical bits, but can be in a superposition of 0 and 1 at the same time. And by entangling multiple qubits, you can perform computations in ways that are impossible for classical computers.
So entanglement is the key to unlocking the power of quantum computers.
It's one of the key ingredients, yes. And the chapter concludes with a glossary of key terms, which is helpful for anyone wanting to dig deeper into these concepts.
Absolutely. Terms like Schrödinger equation, wave function, quantum numbers, degeneracy, spin, the exclusion principle, all essential for understanding atomic structure.
Couldn't have said it better myself.
Well, this has been a whirlwind tour of the quantum world of atoms. We've covered everything from the three-dimensional Schrödinger equation to the particle in a box, the hydrogen atom, the Zeeman effect, electron spin, spin-orbit coupling, multi-electron atoms, the Pauli exclusion principle, X-ray spectra, and finally, quantum entanglement. It's incredible how much we've learned from this one chapter.
It's really quite remarkable how much information is packed into those pages.
And it makes you wonder what other mysteries of the quantum world are still out there waiting to be discovered. What other seemingly bizarre phenomena might hold the key to future technologies or even reshape our understanding of reality itself. Thanks for joining me on this deep dive into atomic structure, and I'll see you next time for another fascinating exploration of the world around us.
Always a pleasure. Until next time.